SwayamPrabha. Digital India. Educated India.
Hello, welcome back to lecture 4, which will be a continuation of lecture 3. So, in lecture 3, we started with the basic equations of theory of elasticity, and then we went to the torsion of shaft with circular cross section. We have discussed the basic features of torsion of circular shaft, and as mentioned, we will now derive the equations of torsion of circular shaft in the context of theory of elasticity. So, as we have mentioned in the previous lecture, the shear stress at any point on the cross section of the circular shaft is proportional to the distance of the point from the center of the shaft. So, let us take any arbitrary point on the shaft. So, which is at a distance r from the center O. Now, at this point R, we have a shear stress. So, let me draw the shear stress. So, the red color one is the shear stress, and as we have discussed, the shear stress is equal to g theta into small r, r being the distance of the point P from O. Now, this shear stress can be resolved into two perpendicular components, one in the x direction and one in the y direction. So, the one in the x direction, let me draw this, and there would be one in the y direction. So, the shear stress in the y direction can be written as tau yz following the nomenclature that we have discussed earlier. Similarly, the one in the x direction can be written as tau xz following the same nomenclature. Now, therefore, we can write and let this angle be alpha. This angle be alpha. So, let us write down the expression for tau xz. Now, tau xz is going to be minus, it is going to be tau sin alpha, where alpha is the angle that is shown here, the angle the point P makes with the x axis. So, tau xz can be written as g theta r, which is the expression for tau, into sin alpha. We also need to put a minus sign because tau xz is now in the negative of the x direction. So, following the sign convention given by the coordinate axis, this will be minus. Similarly, tau yz can be written as g theta r into cos alpha. Now, from geometry we can see that sin alpha is y by r, y being this, and cos alpha is x by r. So, if we substitute the value of sin alpha and cos alpha, we can write tau xz to be minus g theta r y by r, which is equal to minus g theta y. Similarly, tau yz can be written as g theta r x by r, which can be written as g theta x. So, these are the shear stress component in a shaft with circular cross section in the Cartesian coordinate. So, I have the shear stress tau, which is in the radial, which is in the tangential and radial direction. I have converted into the Cartesian coordinate. Now, let us see whether this stress component. So, now in summary, what we can say that a circular cross section shaft under pure torsion has only two non-zero stress component. So, let me write down. So, for a circular cross section shaft under pure torsion, so the only load that we have applied is the torsional moment or the twist moment NT. So, under torsion we can say that all the stress component, all the normal stresses are 0, tau xy is also 0. So, the only non-zero stress component is tau xz, which is minus g theta y, and tau yz, which is g theta x. So, these are the stresses in the cross section of the shaft. Now, let us see that whether these stresses satisfy the equilibrium condition, the three equations of equilibrium. Otherwise, these are not the true solutions. Unless they satisfy the equation of equilibrium, we cannot call them to be true solution, because otherwise the shaft will not be in equilibrium. So, let us see. So, let me write down the equations of equilibrium. So, del sigma x So, let us neglect this part, let us neglect the weight of the body, and let us say that there is no externally applied body force that is acting on the body. So, now let us see, sigma x is 0 for the shaft, tau xy is also 0 for the shaft. Now, tau xz is minus g theta y. So, therefore, the derivative of tau xz with respect to z is going to be 0. Therefore, this equation is satisfied. Now, let us move into the next equation. So, I am neglecting the body forces, and now let us see whether this equation is being satisfied. So, tau xy is anyhow equal to 0, sigma y is 0, tau yz is g theta x. Again, it is not a function of sigma of z, therefore, this whole terms goes to 0. So, therefore, this equation is also satisfied. Let us go to the third equation. Now, let us see this. So, tau xz is minus g theta y. So, this goes to 0, this is not a function of x. Tau yz is g theta x. So, this also goes to 0, it is not a function of x, and sigma z is anyhow equal to 0. So, this is satisfied. So, all the 3 equilibrium equations are satisfied. So, the stresses that we have got for a circular circular cross section shaft satisfy the equations of equilibrium. So, the first criteria is met. So, the stresses that we had assumed for the circular cross section shaft are satisfying the equilibrium condition. Now, let us see whether they are satisfying the boundary conditions. So, let us see the boundary conditions. So, there are 2 set of boundaries for the shaft. One is the lateral surface of the shaft and one is the top and bottom surface of the shaft. Okay. So, we will individually see that whether this stress that we have assumed are satisfying the boundary condition on the lateral surface first, and then we will see whether they are satisfying the boundary condition on the top and bottom surfaces of the shaft. Now, what are the boundary conditions of the shaft? The boundary conditions are 0. The lateral surface, there is no force acting. So, the external forces, surface forces on the lateral surfaces are 0, and the external forces on the top and bottom surfaces are also 0. The only external force or moment that is being applied to the shaft is the torsional moment. So, there is no forces that are acting on the lateral surface as well as the top and bottom surface. So, what is the boundary condition therefore? X hat, y hat and z hat are equal to 0 for the lateral surfaces as well as the top and bottom surfaces. So, let me write down the boundary conditions for the lateral surfaces and see whether it is satisfied. So, what is the boundary condition? X hat has to be sigma x L plus tau x y m plus tau x z n. Y hat, okay, let us first see whether this is being satisfied. So, now I have free lateral surface. So, there is no externally applied force. So, x hat is equal to 0. Now, let us see what is L. Let me draw the cross section and see. So, let me draw, sorry. So, for lateral surfaces, this is the direction of the normal. This is n, this is the normal to the surface, this is the x axis and this is the y axis. So, let n make an angle alpha with the x axis. Now, what is L? L is, what is L? L is cos n x, okay, which is cos alpha. M is cos n y, which is sin alpha, and n is cos n z, which is equal to 0, because the normal to the lateral surface n is going to make an angle of 90 degree with the z axis, the axis along the length of the shaft. So, this is equal to 0. Now, let us see whether with this direction cosine our boundary condition, the first boundary condition is getting satisfied. So, sigma x is anyhow equal to 0, tau xy is 0. Now, n is equal to 0. So, this condition is therefore satisfied. Now, let us move on to the next condition, which is y hat now y hat is equal to 0, tau xy is equal to 0, sigma y is equal to 0, and n is equal to 0. So, this is satisfied. So, let us move on to the last condition. Now, out of this, n is equal to 0 as well as sigma z is equal to 0. This is equal to 0. So, what we are left with is that tau x z into L plus tau y z into m has to be equal to 0. Now, let me write down the expression for tau x z. Tau x z is minus g theta into y into L plus g theta into x into m has to be equal to 0. So, that gives me minus g theta y into sin alpha plus g theta x into cos alpha equals to 0. Okay. So, this is the expression that we have, and now if we go by the geometry that we have seen. Sorry, I have made a mistake. So, this is going to be cos alpha, this is going to be sin. So, L is basically cos alpha and m is sin alpha. So, this is going to be cos alpha and this is going to be sin alpha. So, if we write it down, this is going to be minus g theta y. As we have seen earlier, cos alpha will be x by r and plus g theta x sin alpha will be y by r, and therefore, each of this will cancel each other and therefore, this is going to be 0. So, the third boundary condition is also satisfied. Therefore, the stresses that we have assumed satisfy the force free boundary condition on the lateral surface of the shaft. Now, let us look into the boundary condition on the top and bottom surfaces. Again, as I said, the top and bottom surfaces of the shaft is again free of any applied force. So, if I write down now, let us see what are the direction cosines L, M and N on the top and bottom surfaces. So, L is cos n x, which is going to be 0, because the n on the top and bottom surface is along the z direction. So, it is going to make an angle of 90 degree with the x and y axis. So, this is equal to 0. M is equal to cos n y, which is equal to 0, and n, which is cos n z, is not equal to 0. Okay. N is along z, so it makes an angle 0. So, it is not equal to 0 and it is equal to 1. Now, let us see what happens here. So, sigma x is equal x hat is equal to 0. So, let us see whether this is being satisfied. So, sigma x is 0, tau x y is 0, but sigma x z is not equal to 0, and n is equal to 1. So, this condition is not being satisfied. So, this force free condition on the top and bottom surface is not getting satisfied. We have left with a hanging tau x z. Okay. So, let us see what happens to the next thing. So, I have we see that x hat cannot be equal to 0 on the bottom surface or top surface, and x hat has to be equal to this in order to satisfy the boundary condition. So, boundary condition is not force free boundary condition is not satisfied. So, let us see what happens to y hat. Y hat is okay. So, ideally it is force free. So, y hat should be equal to 0. Now, tau x y is equal to 0, sigma y is equal to 0. Now, n is equal to 1 and this is not equal to 0. So, similar to the x direction force, this boundary condition is also not satisfied. So, I have y hat equals to tau y z remaining. So, this is a concern, right. So, force free boundary condition is not satisfied for the top and bottom surfaces. For lateral surfaces, everything is fine, everything has been satisfied. Now, let us see the third case where I have z hat is equal to now, out of this z is equal to 0, ideally it is a force free thing. So, tau x z is not equal to 0, but L is equal to 0. Similarly, this is not equal to 0, but M is equal to 0 and sigma z is equal to 0. So, this is satisfied. So, only the z direction boundary condition is satisfied, whereas x and y direction are not satisfied. So, now how well then how can we say that the stresses that we have assumed is satisfying the boundary conditions on the top and bottom surfaces. So, it is said that ideally or theoretically the torsion that is applied to the shaft should be applied in such a way. So, let me spend some time here and explain this. So, on the top and bottom surfaces, the externally applied load x and y should be applied in this form. The distribution of the externally applied force should be of this form, so that this condition and this conditions are satisfied. Okay. But practically it is not possible. So, this distribution of the load will give net x to be 0, net y to be 0. You see, this will always be cancelled by a diagonally opposite point. So, net x will be 0, net y will be 0. So, this condition and this condition will be satisfied, but they have to be distributed in this way. But what will they produce? The net forces will be 0, but they will produce a net torsional moment mt. So, the resultant of applied force like this will produce a torque mt, as you can see from the distribution of the force. So, this is going to produce a torque like this. So, in order to satisfy the boundary condition perfectly as per theory, the torque that is applied to the shaft, as I have said, the torque that this mt that is applied to the torque to the shaft should be applied in this form. But in practical case, it is not possible to apply torque in that form. But in practical or real life case, it really does not matter whether you apply the torque as a pure torsion or in form of this force distribution, because the boundary effect according to Sandbenen's principle will be nullified at the region close, will be effective at a region close to the boundary, and at the inner region the boundary effect will not be prominent. So, in other words, we can say that if we have a shaft, whether we apply a pure torsion or we a pure torsion mt like a pure torque, or we apply mt in form of forces like this, the effect will be seen only in a very small portion near the boundary. In the inner regime, in the inner portion of the shaft, the effect, whether we are applying a pure torque or a torque in form of this force, will not be visible. This is according to the basic theorem that we have studied in solid mechanics, which is called Sandbenen's principle, which states that the boundary effect are seen only in the region close to the boundary and not in the inner portion of the structure. So, now therefore, we say that the stresses that we have considered, that is sigma x equal to sigma y equal to sigma z is 0, tau x y is equal to 0, tau x z is g theta y, tau y, sorry, this is minus g theta y, tau y z which is g theta x is going to satisfy the equilibrium, this is going to satisfy equilibrium condition, boundary conditions on lateral surfaces, boundary conditions on top and bottom surfaces with practically true way. Theoretically, it might not be satisfying, ideally it might not be satisfying the top and bottom surface, but practically we can say it satisfies the boundary conditions at the top and bottom surfaces. So, with this I will end this lecture. In next lecture, we will move on to torsion of non-circular shaft and we will see how it is different from the torsion of circular shaft. Thank you.